Hey guys, let's talk about exponential growth today. Before we talk about exponential growth, let's talk about other types of growth first. First one we'll talk about is linear, which is right here. And linear is really, you have an equation like a line, y equals mx plus b. So our slope here is 2 and our y-intercept is 0. So here's our function for our linear growth model, which is 2x. My computer is being a little laggy right now. Just give it a second. Okay, then over here we have our polynomial growth model. And that guy is just anything that has x to some power. All right, so maybe 3 plus x squared, something like that. Okay, so for us, for this example, our polynomial growth model is just x squared, y equals x squared. So let's see what happens when we start plugging in numbers into these two different models. When we plug in 1, we get 2 and 1. When we plug in 2, we get, well, both of them are 4. When we get 3, we get 6 and 9. And for 5, we get 8 and 25. So clearly at first, the linear model was winning. Then the polynomial caught up. And then the polynomial started winning, right? So we can say that at first, the polynomial grows a little bit slower, but then it eventually catches up and it exceeds the linear model. So how does exponential growth fit into this? Well, what we're going to do is we're going to look at the same thing. We're going to feed 1, 2, 3, and 5 into an exponential function. Now, this is our exponential function. An exponential function differs from a polynomial function. As you can see, the x is not the base. See here, our base is x, but x is in the exponent for our exponential function, right? So this is an easy way to tell whether a function is exponential or not. And we're going to do the same thing. We're going to feed these same numbers in. We have 1 gives us 2. So at this point, we're pretty much tied with linear. When we plug in 2 for x, so I have 2 squared. All of them are equal. They're all 4. When I plug in 3, I get 8. Still, polynomial still in the lead, exponential second, linear is the smallest. And when I plug in 5, look what finally happens. Our exponential curve, it starts to win. It's 32, then the polynomial, then the linear. So for greater values of x, the linear model loses, the polynomial gets a little bit ahead, but the exponential is always going to be winning this fight. And as you pick larger and larger numbers for x, this exponential function starts winning, not just by a little, but by a lot. So let's look at what happens if we plug in, I forgot what I picked, 100 into our function. So for our linear function, we plug in 100. So I plugged in 100 for x, I get 200. For my polynomial function, if I plug in 100, I get 10,000. So 10,000 is way, in my opinion, it's way bigger than 200. So what happens if we put 100 into our exponential function? Well, we get this number, 1.26765 times 10 to the 30th power. So what that means, it's this number, 1.26765, with 25 zeros after it. Now, obviously I didn't do all the zeros, but I think exponential has won by a huge margin here. So that's the thing that's so special about exponential growth. It grows very fast, very quickly. And now, ironically, this comes to our conversation with the coronavirus, right? Why do they all want us to do social distancing? Because viruses spread not linearly, not through a polynomial model, but they grow exponentially. So every 2 people that come in contact with someone else that has this virus they have a high probability of getting this virus as well. So this is the scary thing about corona, right? It's just going to spread into the population very quickly. So what do we do to counteract this? We're going to limit our social interaction and probably slow down the rate. I mean, probably we're all gonna, well, majority of the population will eventually have some form of it, but this is why it's so important that we listen to the people we need to listen to and not be fools and go running around touching our faces on surfaces and stuff like that. Anyway, exponential growth is a powerful thing. So let's look at their graphs, the linear model, polynomial model, and exponential model. So here is how they grow. So this guy right here is our linear model. You see it's slowly creeping up the y-axis. Now, polynomial, this guy in blue, he actually does a very good job of getting to a high number, but let's see. He reaches this number when x is 20. So he reaches 400 for when x is 20. For our exponential function, he reaches 400 when it's, I don't even know, less than 10. So this picture really shows us how quickly exponential growth works, how quickly it can escalate. So always remember it's in this order: linear, smallest; polynomial, second; exponential, fastest. All right, so moving on. So we're looking again at 2x, or 2 to the x. 2 to the x is an exponential function with base 2. We know it's exponential because x is in the exponent. Anytime you have an x in the exponent, this guy is growing exponentially. It's going to its y values are going to start spitting out really large numbers for rather small numbers of x's. So we have a general formula for exponential functions. So the general form for an exponential function looks like this: f of x, or y, equals b to the x. So y equals b to the x, or f of x equals b to the x. The thing about exponential functions is that this base b, has to be a number greater than 0. So we can't have something like this. Oh, sorry. We can't have something like this. We can't have a negative as our base. No negatives. We have to pick numbers that are greater than 0. So this is okay. This is not okay. Alrighty. And here are some characteristics of exponential functions. The first one is this: the domain. The domain is all the x's that I can put into my function. So if I have 2 to the x, I can put whatever number I want in for x. I can do 100, and I can do minus 100, all right? So it doesn't really matter. I can pick any number between minus infinity and infinity. Let's look at our range, though. Our range is a little bit different. Our range, meaning the y values that will come out of this function. So my range will be between 0 and infinity. Now, if I have a positive base, like 2, and it's raised to some power x, is there a number that I can plug in for x, maybe like 2 or 2 to the pi, anything, that will make this number, that will make my y value negative? No, there's no such number. Also, there is no number that I can plug in for x that will make this whole thing equal 0. 2 to the something will never equal 0. I hope that makes sense to you guys. There's no number that I can raise 2 to that will make it equal 0. That's why our range, the y values that I can get for this function, are always going to be 0 to infinity. Okay, another thing is that the point 0, 1 is always on the graph for a basic exponential function that has the form b to the x. And why is that? Because, well, anything raised to the 0 power is always going to equal 1. Okay? Anything raised to the 0 power is always going to equal 1. That means if I plug in 0 for x, I'm going to get 1 for y. So this point is always on our graph. Okay, and here's the last one, and it's probably the most important out of all of them, which is my function is 1 to 1. And what is 1 to 1? If you guys remember, we spoke about it a long time ago, is that 1 to 1 means that for each input of x I put in, there's a unique output I get. So remember we had functions like x squared, and I drew those two eggs for you guys. And I said if you put in, I think this is the picture that you guys remember. Hold on. Boom. I said if you plug in -2 and 2, you get 4. 1 to 1 means that this case will never happen, that every unique x goes to some unique y. And why is that so important? It's because it passes our horizontal line test, and that means it has an inverse. And this is going to become really important in not the next video, but the following video after that, when we start talking about logs. So again, our exponential functions are 1 to 1, which means they have an inverse. All right, so let's go ahead. Let's start graphing one simple exponential function. Let's look at this guy right here. 3 to the x. That's what we're trying to graph right now. So I already went ahead and I chose several x's for us. I chose -3, -2, -1, 0, 1, 2, 3. And I plugged it in right here. Let's start from the bottom here, okay? So 3 raised to the 3rd power. Actually, let's start in the middle. 3 raised to the 0, we said anything raised to the 0 power is 1. 3 raised to the 1st power, that's just 3. 3 squared, 3 cubed is 27. Okay. Now, the next part gets a little bit more tricky. You have to remember some of these rules. So 3 to the -1, how do we deal with that? Well, how you want to deal with it is pretend that there's no negative there. All right, so you see this negative, just pretend it's not there. So what would be 3 to the 1st power? Well, that's just 3. So we know that it's 3, but the second we know, because we know that there's a negative in the back of our mind, we're going to flip it to the denominator. So what do I mean? Instead of having 3, we put that 3 in the denominator. So we're going to follow the same rule for 3 to the -2. I'm going to pretend like the negative's not there. So 3 squared is 9, but because it is negative, I'll put it in the denominator. So first pretend like it's not negative, and then think about what the negative does. So 3 to the 3rd is 27, but because it's -3, put it in the denominator. And it's not always in the denominator. It's just the other side of the fraction. Meaning, if I had 1 over, actually we're going to do it next. Never mind, we'll do it in a second. We'll talk about it in a second. Okay, so I'm going to go ahead, I'm going to plot these points. Let's just say this is 1 over 27. This is 1 over 9. This is 1/3. This is 1. 3, 9, 27. And I'm just going to scooch it down a little bit, just so it makes a little bit more sense. 1 over 27, 1 over 9, 1 over 3. All right, well, you guys will get the picture. So at 3, minus 3, I have this. At minus 2, I have this. At minus 1, at 0, I have 1, 3, 2, I have 9. Okay, I did a terrible job. Let me fix this. Oh God. Come on, computer. Work. There it is. Okay. So I'm going to scooch this down just a hair, just so it looks a little bit better. So here's 1. And wow. Okay, maybe I should have done a little bit of a better job with this. And like this. Well, either way, it's going to look kind of like this. And it's going to quickly skyrocket right here. All right. So there are things to note here. The right-hand side, I know it looks ugly, but still, follow me. The right-hand side, this part, eventually, or where do my y values go? Well, they just keep increasing and increasing and increasing. So they eventually go to infinity. And what happens here? What happens to the left-hand side? Well, as I pick smaller and smaller values for x, my numbers are going to get smaller and smaller and smaller and smaller and smaller for y. However, they never hit 0 because of this rule right here, right? What we spoke about before. There's no number that I can raise 3 to that will make it 0. So this arrow right here gets very close to 0, but never 0. So there's actually a horizontal asymptote at y equals 0. This x-axis is a horizontal asymptote. Our graph will never touch it. Okay, so let's do another one. Let me just erase some of this stuff. All right, so now on the other side, I have 1 over 3 raised to the x. And again, I pick the same x values. So let's start with the positive ones first. So I'm down here. Let's start with 0, the easiest one. So anything raised to the 0 is just 1. Anything raised to the first power is just itself. Now, how do we approach 1 over 3 squared? Well, anytime you have a fraction squared, so if I have like a over b squared, this is equal to a squared over b squared. So this guy is actually equal to 1 squared over 3 squared, which is just 1 over 9. Same thing here, because I have a 3 on the top, 3 in the exponent, sorry. I'm going to raise each the numerator and the denominator to the third power. So I'm not going to say that. It's going to confuse you guys. So I have 1 over 27. So now let's look at the negative cases. In this case, I have a negative 1. Well, we said that if it were positive, my result would be 1 over 3. But because this is a negative 1 in this instance, what I'm going to do is I'm going to take this 1 over 3 and I'm going to flip it. Just like I did in the previous example, I'm going to flip it. But this time, because it's already in the denominator, it's going to go into the numerator. So it looks like this. So I flip it because it has a negative exponent. Just like how I flipped it in, where's that other guy? Just like how I flipped it here, right? 3 squared equals 9. But because it's a negative, I put 9 on its head. I put it in the denominator. And for this one, 1 over 3 to the first is just 1 over 3. But because it's a negative exponent, I flip this guy over and he becomes just a 3. So the same concept applies for the rest of them. I take for minus 2, I take the answer that I have here, which is 1 over 9, and switch my numerator and denominator. So this will equal 9, and therefore this will equal 27. So if you graph this out and make it look pretty, you'll realize that, sorry, let me just erase this. You'll realize that, come on, it'll look something like this. Again, this is not a very good exact. Oh gosh, it's actually very bad. So it should look something like that. Just pretend it. So it's everything in reverse, all right? So if your base here is some number greater than 1, your graph will go up in the right and down in the left. However, maybe I should have switched letters there. Boom, boom. However, if your base is between, if B is between 0 and 1, so like 1/3 is between 0 and 1, then your graph will go up in the left and down in the right. Okay, so in the next section, we're going to be talking about compounding interest and interesting things from there. All right, see you in the next one.